happy to have Roman.
All right.
Okay, so today we have Roman Poberezhniuk. He's a postdoc at the University of Houston, working with myself and other collaborators, and he will tell us about the measure revisited after 20 years, probing QGP with charge fluctuations at heavy ion collisions. So Roman, please.
Thank you. So my talk is based on the recent preprint, which is done in collaboration with 4 researchers, 3 of whom are in this room. So let me start by saying that hadrons compose of quarks, and on the phase diagram there is a transition between million plasmas of deconfined matter and hadronic matter. And we are interested in the region of phase diagram of small chemical potential, where LHC data lies, and where theory predicts this transition to be a smooth crossover. So the main idea is such that hadrons carry integer electric charges while quarks have fractional electric charges. So if you imagine a grand canonical ensemble, so some subsystem in coordinate space with charges that can freely fluctuate in and out of this box, and we are measuring fluctuations in this box, then in the case of quarks, fluctuation should be smaller than in the case of hadrons, because they have fractional charges. To quantify this, the observable was proposed 25 years ago here at Berkeley, called TeV measure. It is variance of electric charge normalized by total charge particle multiplicity and multiplied by 4. It was
Just maybe a question to figure why the factor 4, where does it come?
Oh, because in the trivial quark-gluon plasma you get 1, and in the other one you get 4. That was it. That was
So you wanted the baseline to be the QGP.
Exactly. Right.
All right. I see.
Yeah, so it was estimated that in hadron gas the measure equals approximately 4, and in QGP approximately 1, in grand canonical ensemble limit.
So is it for analytical result?
Yes.
Yeah.
If you say that the end charge is really the entropy and you work it out in the Boltzmann limit, you get 1 for the quark-gluon plasma and 4 for pion gas. Right? But this is no interactions, nothing, and no Fermi statistics, just simple.
No, I see. So
as
it's
simple
not
as you
real.
can do it. Yes.
That's why it's because there are no equalities. That's why I'm asking.
Yeah. That's probably, if you do it a little bit better, it's not equal, right?
I see.
In hadron gas, it's 3 roughly, right? He will probably talk about
Yes,
this.
I will talk about that. So the measure was measured on ELIS and RHIC, and was calculated in transport models. But there has been no quantitative prediction for QGP case. And so the conclusion remained elusive. And here we solve this problem. So we calculate the measure on equal grounds for QGP and hadron gas cases, so we can compare them.
Can I still ask? So the middle one is the, as there was a discussion. So this is the theoretical estimate, right? And then on the left-hand side, this observable is calculated from the final state hadrons, right?
Correct.
And then how can we still see this, like the TeV measure in the final state? Like how is it connected?
So calculation for hadron gas are done in transport models. So
But then
So the argument was very simple. Look, I mean, when you do a first paper, you can be always very sloppy, right? So this D measure is essentially the ratio of this variance of the charge divided by the entropy. Now, if I have an expansion, the entropy is conserved, entropy density, right? Okay. So whether I'm in a quark-gluon plasma or at the end, I have the same denominator. And now, since charges are conserved in each event, right, the charge stays the same, right? Except for charges which scatter in and out of the acceptance. So if you make the acceptance sufficiently large, this correction is not possible. That's why that's when we discovered the use of conserved charges, because you need diffusion to change them, right?
Yeah, so situation heavy ion collisions is different from ground canonical ensemble. So in ground canonical ensemble, fluctuations are measured in coordinate subspace, while in heavy ion collision, momentum cuts are performed. In ground canonical ensemble, subvolume should be much smaller than the total volume, so charge conservation effects are absent. While in heavy ion collision, it is not achievable, so the measured subsystem is comparable in size to the total system. So we must take into account charge conservation effects. Moreover, due to the rapid expansion, there can exist causally disconnected regions of the fireball in which charge is locally conserved. So we need to take into account local charge conservation. So we start from ground canonical ensemble. But then, on top of it, we incorporate these other effects, like resonance decays, local and global charge conservation, and momentum acceptance cuts, which are relevant for heavy ion collisions. So let's start with ground canonical ensemble. In ground canonical ensemble, variance of conserved charge is proportional to the second order net charge susceptibility. In ground canonical ensemble, we decompose this net charge susceptibility into scalum baseline and a correction which encompasses two particle local correlations. Before decays, so first we turn off the decays and we parameterize the strength of these correlations by a single parameter omega, which encompasses relevant correlations and which distinguishes in our model QGP from hadron gas case. So this is the main parameter which we are trying to extract. Secondly, we need also to include resonance decays, which increase numbers of charged particles and introduce additional correlations between them. And in the end, we arrive at the following parameterization, which is really equivalent to just the definition of second order charge susceptibility, but it decomposes it into self-correlations and two particle local correlations. So, it contains this free parameter omega, which we are trying to find. And resonance decays are characterized by parameter gamma. At LHC, it is just one number, and we estimate this number in hadron resonance gas model using thermal fist package. So let us now focus on the case of hadron gas. And in hadron gas, we estimate parameter omega using thermal fist model also. So really at LHC in hadron gas, so at chemical result, omega should be close to 1. But really, due to the presence of multi-charged hadrons and Gaussian statistics, it is slightly higher than 1, and we estimate it to be 1.1.
Excuse me. Just a simple question. So, this 1.1 is a result of statistics or result of multi-component system?
It's a result of multi-charged hadrons. So, because they carry like not integer but even high electric charge, they increase fluctuations.
Yeah, because I remember that even without any charges, if you have the system of particles with different masses, you would obtain slightly larger results.
No. It's, I guess it's both effects here, but the fact that there are hadrons which carry 2 units of charge and not 1 makes different contributions to kappa 2 in numerator and to denominator.
Mm-hmm.
Basically the
Yeah.
same mechanism which I mean.
No, but if you have 2 components but each carries just 1 charge, then they have same contributions.
I just remember our article about gas of different masses and we observe the same
No,
effect.
masses have nothing to do with this.
Yeah.
It's the charge
I
is
understand.
bigger.
And both Einstein.
Yeah.
There are pions which are bosons and then enhanced.
Yeah. Okay. So it's just 2 effects.
Yeah, so in QGP it is more complex. To estimate non-canonical fluctuations, we multiply and divide by entropy. We assume isentropic expansion, and we use data from several different sources. So first of all, we considered first the limiting case, if fluctuations result in pure QGP. And for that we use a Stefan-Boltzmann limit. Secondly, we use estimate of entropy over charge multiplicity at LHC. And gamma Q is obtained from hadron resonance gas. And at the end, we get a number which is 3 times smaller than for hadron gas case.
So just to clarify, so what's the issue here originally, right, with QGP? That we don't know charge multiplicity of hadrons in QGP, right? Like, why do we need to do all of this? To do these 3 factors. That we need to somehow convert entropy of QGP into charge multiplicity, right? And in hadron gas, it's straightforward. You already have charge multiplicity because it's a hadron gas that we measure. And then in QGP, we don't know what it is, right? So,
Stefan-Boltzmann limit here is usable because
it's a limit.
Limiting case. Because you do it.
no, okay. So what you're saying is that it's just limiting case. So
Yes.
So the general case. In general case, instead of Stefan-Boltzmann limit, we use latest data.
okay. Then I understand.
And we get a temperature dependence of omega.
Now that's can you go 1 slide back? I mean, there is then this ratio of kappa 2 over entropy density, and this you can read off from the
Chi2 over S.
Yes.
So yes, this is the general case using latest data. And sanity check here is that at chemical result, it approaches hadron gas estimate of 1.1, and at high temperatures, it approaches Stefan-Boltzmann limit.
Yeah, and it still shows this large difference.
Yes. Mm-hmm. And of course, when we did this, it wasn't a smooth curve, it was really a jump. But this these things have changed with improved
So yeah, from here, so if we extract the value of omega, then we
So this omega is the d measure divided by 4.
Yes.
Okay.
Almost.
Almost.
Okay,
Yes.
okay. So I got a bit confused
so
with that.
omega is in ground canonical ensemble. So it is for ground canonical.
Yeah, it's the measure in the grand canonical limit
Exactly.
divided by
Without
4.
decays.
Exactly.
Yeah, without resonant decays.
So if we extract its value, we can say at what temperature charge fluctuations result. Yeah, so also we need to incorporate charge conservation effects, in particular local charge conservation, and historically it was done using truncated fireball approach. So the fireball is truncated, and this VC is a correlation volume of the truncated fireball. So this is the effective method to quantify local charge conservation. But we are using a newer, more advanced approach based on density correlators.
I may just add here that the truncated fireball was done only for hadron gas as well. So not only it was truncated fireball, you would not do QGP with it. That's one of the limitations.
And we didn't do this at all, we just did global.
Yes. So density correlator is decomposed into local correlation part and a balancing contribution, which balances, which accounts for long-range correlations due to charge conservation. And this balancing part is modeled by Gaussian in coordinate space. The unknown parameter here is sigma, which is the weight of Gaussian. It can be mapped to correlation volume, but the method provides more precise acceptance dependence. Namely, it better describes Alice data on net proton fluctuations. And from this data, it was extracted the value of sigma 0.78, fitted to net proton data.
That is baryon conservation, right?
Yeah.
So this gives us something to work with, but it's also not necessarily charge conservation, I guess.
Yeah, so for charge conservation, the value of sigma may be different. So we use it just as an example. So this parameter sigma, if it approaches to infinity, so the weight of Gaussian approaches infinity, it corresponds to global charge conservation.
So if this local charge conservation is imprinted on the system, on the quarks, on the quark-gluon plasma side of things, shouldn't I then? I mean, then I have only quarks, and the charge carriers and the baryon number carriers are the same. So would that mean I should use the same sigma? Never thought about this.
No.
But because the naive idea I always had, it should be a wider for the charges, because you have the pions which can diffuse further out, but if the charge conservation is imprinted early.
But do they diffuse same way in eta?
Well, I don't know. That's why I
Compared to
ask the
rapidity,
experts.
right?
Yeah.
I don't know either. Because it's Hydra doesn't yet know
Right.
about degrees of freedom, I guess.
But still, I mean, in hydro, there should be no difference, right? Baryons, it's all about quarks, whether it's eta or rapidity, right? I mean, your thing lives in eta space,
Yeah.
right?
Yeah, it's.
I mean, when you do the smearing later on, the thermal smearing, then you get something else, right?
Yeah, you get ions scattered.
Yes. All right, sorry,
No.
it just popped up.
At infinite local conservation weights, we get global conservation. To get variance of electric charge in a subsystem in coordinate space, we need to integrate two-particle density correlator over volume. And in the case of global conservation, we reconstruct subensemble acceptance formulas, which connect the fluctuation in the subsystem in coordinate space with ground canonical fluctuations. But we are interested in a more general case of local charge conservation and of momentum cuts. So we also use a blast wave model, which gives us acceptance probability that a particle emitted from some coordinate, some spatial rapidity will end up in a given momentum acceptance. For that, we use blast wave model, which is a standard model for this LHC. So we put everything together and we arrive at final formula for d measure at LHC. It contains three terms. So the scalar non-interacting baselines, and there are two-particle local correlation and long-range correlations due to charge conservation. Here, this P eta is acceptance probability of particle emitted from coordinate eta. The formula contains two free parameters. One is omega, which we are trying to estimate, and the second is sigma, which is included in this two-particle acceptance probability.
So this P of eta, why is that not a parameter or something?
So particles are measured in acceptance subspace.
Yes.
So we need to know, but we are working with coordinate subspace.
Yes.
So we need a connection. We need to know which particle will be accepted. And this is given by P eta.
Yeah, but P eta must depend on the temperature somehow, right?
Yeah. And
it must depend on the particle mass somehow, right?
Yes, and it is all included in the blast wave model.
All right. Okay. So in that sense, it's not a parameter, but it's in the blood. Okay.
Mm-hmm.
So because that brings us back to the baryons versus pions, right? When you, I mean, even so, you would, if you had quark charge conservation, you would keep your sigma the same, but the P eta would change. It would be different for protons than for pions, right? Because of different mass.
Mm-hmm. Yeah, we take this into account.
Okay.
Yeah, so this is the final expression. And we can compare it to LHC Run 1 data. For omega, we use two limited cases, 1.1 and 0.36. So it corresponds to hadron gas and QGP. And hadron gas is depicted by blue color, while QGP here shown by red color. So this blue and red, they differ by parameter omega. Then we take different values for the other three parameters, sigma, so for locality of charge conservation. We consider global conservation, which corresponds to solid lines. Then we take the value of sigma 1.2, which is a standard value historically used at LHC, and even more local conservation, 0.78, which was extracted from net proton data. So 1.1 is a dashed line, while 0.36 is a dash dotted line. So first of all, we see that QGP case is much less sensitive to how local the charge conservation is. Secondly, we see that hadron gas case describes data only at the most local charge conservation, while QGP scenario reasonably describes data at any value of sigma.
So that's one can see from the formula this why sensitivity is so different between QGP and hadron gas to sigma.
Yeah, so in QGP, this parameter omega is smaller.
Mm-hmm.
And sigma sits in this
Third term.
yes, third term. So it's multiplied by omega. So small omega is sensitivity small. And even the shape of the data is like.
Right. Okay, go on. Keeps us late. I didn't do anything.
So, even the shape of data is better described by QGP case. Also,
So, excuse me,
Yeah.
maybe I don't understand it pretty well. I can see here that if you would consider, let's say, I understood that all these lines are inside of this 3 sigma interval. But if you would look at the errors, it seems that the global conservation line is the best one to feed the data. So what is the reason for it? I mean, I would expect that local conservation should be better, to be honest. Because global conservation, I'm not sure that is the case.
They both are within errors. So.
And the errors are highly correlated.
Oh yeah, that's a good question. So that's the reason. Okay. But this error estimation, maybe you know if it's a good one or not.
It was done over 10 years ago, so. Yeah.
We are not supposed to judge.
Exactly.
so regarding errors,
Yeah, my point is that if errors are, like, if you would count them correctly, they would be larger than my questions for this, but yeah.
so regarding these errors, Alice presents corrected D measure, which uses 2 corrections for global charge conservation. So D prime and D2 prime. Then they take the mean of these 2 corrections. And we argue not to do it, just to present uncorrected D measure, because first of all we need to uncorrect it and correct it again.
Makes sense.
Secondly, it increases substantially error bars, so the information is lost.
Yeah, part of this, presumably part of maybe even the large part of systematic error is the difference between D prime and D2 prime,
Oh, I see.
which is in principle not needed at all.
And D prime is now, or even the proponents of D prime agree now this is maybe not the right thing to do.
Yeah.
I see. Thank you.
So to quantify how much QGP is preferred by the data, we perform Bayesian analysis in the space of these two free parameters, omega and sigma. For omega, we use uniform prior. For sigma, we use two priors. One is uniform. Second is very local conservation, so 0.78. So this is corner plot. These are posterior probabilities. So taking into account the data. This is joint probability.
So where's sigma? I don't see sigma here.
Sigma is VC over V tot.
Okay.
So it is just another
Okay.
quantitative. So this is joint probability, and these are marginalized. So this one parameter integrated out. For sigma, we see that posterior distributions look a lot like priors. So it indicates that D measure is not very sensitive to locality of charge conservation. And for omega, for the uniform prior case, we see that the median value is 0.34, which corresponds to pure QGP case.
And what is H1, H2 here?
H1.
In the table.
It's just two hypotheses. So one hypothesis is QGP, second is
So it's not
hadron
H1,
gas.
H2, it's hypothesis 1, hypothesis 2.
Yeah.
I see.
Yeah. So, and to estimate how one hypothesis is preferred in comparison to another hypothesis, there is a quantitative bias factor, which we calculate. And bias factor for uniform prior is 9.7, which according to the classification of scientific evidence corresponds to moderate evidence on the border with strong evidence. Now, in the case of local conservation prior, bias factor is smaller. It is moderate evidence on the border with weak evidence. So we claim that we obtained moderate evidence of result of electric charge fluctuations in QGP phase at LHC. Now we also present predictions for LHC Run 2. And some data, preliminary data, is already available for Run 2, namely ELIS. And here we see that, as before, data in the case of HRG is described only when charge conservation is very local. But in the case of QGP, now data lies higher than the prediction. So QGP case describes the data only at global charge. So when charge conservation is global. But data is data and it is subject to change. So we don't incorporate it into our analysis for now.
It's preliminary data, right?
Right.
Yeah.
And it's still decorrected.
What?
It is still decor.
Yeah, despite us arguing, ELIS presents corrected D measure.
Oh,
The primary double prime included.
okay. So we have to.
So hopefully they publish it without this correction.
Right. But what correction is it again? The mix? of the two?
I think so,
Or is it just you?
but I think it's the
But how come then the error bars are so small? That is okay. All right. Everybody's close. We should. Well, let's wait till the paper's out, then we can criticize. Okay.
So yeah, in conclusion, we performed quantitative calculation of charge fluctuation for QGP and hadronic scenario. So to achieve this, we incorporated global and local charge conservation, resonance decays, momentum acceptance. We obtained modern evidence of results of charge fluctuations in QGP phase. We presented predictions for LHC Run 2. We are looking for LHC Run 2 data to refine this result, and formalism can be extended to conditions. Thank you for attention.
questions.
So, I think really outside question, if anybody. So how the experiment measure this?
Sorry?
How experiment measure this? How they get the data point?
How they measure it?
Just do it.
So they measure charge particles.
Okay.
Um,
How they calculate the fluctuation?
oh,
What's the measure?
is it the D measure?
Yeah.
How do they measure it really, practically?
Yeah.
What do they
Do
do?
you use this new dynamic?
So they pion count proton tracks event by event
Okay.
and event by event distribution.
Event by event distribution of what?
So net pion plus net kaon plus net proton in final state, that's the net charge.
Do they like that, or they just look at charges? Do they do quark-gluon?
Yeah, probably. No, actually, I think they actually do charges. Yes. So just charge tracks. How many tracks each event?
So they have positive
goes
charge,
this way,
negative
negative
charge,
charge goes the other
Yeah.
way.
and then
They take the difference and the sum. They take the rapidity interval, and you
so that is the eta curve they have, right?
Yeah.
right.
So this is within the jet or
No,
just
no, the whole file.
or within the whole file?
Well, there is a cut in
In
PT, right?
rapidity.
In
In
PT.
Rapidity.
Rapidity between two particles
No, you just have an acceptance volume in PT and in rapidity, right?
or PT and rapidity?
All right, and then you just
count
count.
everybody.
You count everybody.
You count everybody and how you do the fluctuation.
Well, for each event you count the number of positive charges, number of negative charges,
Okay.
and then you can do for each event the difference, which is your net charge.
So that's
And then you do this for all events, and then you have a distribution of the net charge, and then you do the
Yeah.
moments of that,
moments of that.
right? The variance in that case. And the total charge is easy, just take the average of the sum. Event average, right?
Yes, so maybe a naive question, but so in your formalism, you're looking at the D measure in pure QGP matter and also pure hadronic matter, which I'm assuming is like the whole particle list.
Not only in the fluctuations can freeze out at any temperature. And it would correspond not to QGP, not to HRG, but to something in between because it's crossover.
That was going to be my question. Okay, thanks.
But when you plug in your omegas, it's either one or the other. No, when you do the Bayesian, not. Okay.
When we do Bayesian, we obtain
That's right.
like in general
Something in between.
value.
Yeah. Fair enough. Yes, yes.
The corner plot has everything in between.
Right.
But the bias factor compares to limiting case as well, right? So in principle, you could have something in between as well.
Right. Okay. Yeah, that was what I was getting at.
So maybe back to Walker's formula, I'm still kind of confused. So you have Q square average minus average Q square.
Yes.
For the variance.
Yeah, the very beginning, yeah, that's right. So the Q square is not your, I mean,
Well, if you
what's the Q square definition?
It's the charge in a given event. and then you take the expectation and you square it, right? I mean, that's what you. So you take your events, in each event you
But the
calculate.
charge is positive and negative, right?
Yes,
So
that's why you square it. You get the
even
variance.
even for the subtraction term also.
Well, I mean, in principle, this is very small what you subtract.
Ah,
Right?
okay,
I mean, it's
okay,
essentially
gotcha.
zero LHC.
Oh, yeah, that's what I was.
Right, it's the first term is where the action is, right?
Yeah.
But officially, the variance is that. Of course, in this case, it's just the square.
Gotcha. Okay, so that now I understand the experiment can do that.
And since you square it, you pick up the fractional charges. That's
Yes.
But
Yes.
people actually, this way they measured, for instance, from shot noise, they measured actually the fact that Cooper pairs of charge too, that has been actually used. Kitazawa found this reference.
So that's how you compute the QGP because you have a fraction charge. and
Exactly.
so on.
So
Okay.
you get one squared versus a third square.
That's
That's where the action comes. That's all there is.
Okay. Thank you. Thank you.
I guess I also have a new question. Why correlations don't play any role here in the distinguishing the QGP from the not QGP? I mean, in sense you have charged, positive and negative charged part of the system, right? I would expect that they should be correlated. And my question is that I understood that in general it might be small or something, but it might be interesting to look how the correlation functions between plus and minus behave. Can you say that, I don't know, let's say they are very small and we don't care about them, or can you say that it's just off topic, so that's why we don't care about them?
So we have this parameter omega. So we consider only second order system.
Yeah.
So it is sufficient to have one parameter which quantifies the deviation from scalar baseline.
Sure, but this is my question. My question is that if I would ask what about correlation between plus and minus, can you say that it's independent either we are in QGP or not? Or can you say that
So
we're not interested in it?
So we are interested in it, and for instance, when you have a resonance decay, it gives you a correlation between plus and minus. It increases fluctuations, and
then here they are totally range, so you don't have any cross terms.
No, they all averaged out. The
Yeah.
phi 2 has all of them.
Okay.
We have plus plus, minus minus, and plus minus. They're all sitting in this phi 2 cube.
I see. So you consider them, but basically not invariants.
Not separately plus minus. You need
Yeah,
additional assumptions to get it.
But they are sitting there, and
they are there.
that's, I guess it's answering my question that they are not neglected.
No, they're not negligible. But they averaged with other pairs. Because only then you don't need to assume anything else.
Yeah, but in general, you cannot say that they would deviate for the case out of QGP.
Well,
and even
we don't really know what they are in QGP actually.
I see. You cannot measure them. And, yeah. But you can find them from your formalism, right?
Well, in QGP no. Because you need to convert 1/3 to unit charges and then construct plus minus correlation. So that entropy conservation is not enough to do that anymore, I think.
I see.
So,
Can I see the lattice plot again? That was omega, right? So what you used for the quark-gluon plasma is the asymptote there, right? I mean 0.36 or something like that, right?
Yeah.
But if I think about a heavy ion collision, it's sort of an average, or even if it's in the quark-gluon plasma, it's something between, let's say, whatever 150 is the transition temperature. So it's some average between 0.3 and 0.8, right? So shouldn't one expect when you do your Bayesian that you should, I mean, that your peak should be sitting somewhere in between? I mean, just from, I mean, unfortunately, as I said, before the life was easy. There was a first order type transition and then it jumped from 1 to a third or whatever that is, right? Now we have this smearing there and the lattice even if I have the lattice, right? I mean, would suggest I should be somewhere by the eyeball 0.6 or something like that.
And we obtain for uniform priors, and the most probable value is even less than Stefan Boltzmann.
All right.
Just the Bayesian,
Well, it's
depending on the error
consistent
bars.
with this.
Right.
The error bars really give us.
No, but I mean, it has long tail though.
But
The
it's not-
Bayesian plot.
Okay.
So it goes all the way to hadron gas.
Right. Yeah. But what I mean, but from that one would not expect 1.1 and one would not expect 0.3,
Yeah.
but some sort of clever average where I run hydro through and where this stuff then sort of
Yeah,
gets settled, right?
I guess.
Yeah, we will work on it. We will.
No, just, I mean, I'm on the paper, I just realized this now when you give the talk, right? I mean, we could have written this in the first paper as a remark, right? But
Yeah,
now when we get it back from the referees.
Does the hydro actually change it?
What?
Does the hydro will modify your?
Well, no, hydro doesn't because, I mean,
So that's fun. So that means you I heat the highest temperature possible, and then you go down.
no, the question is where are the charge fluctuations frozen in, right?
That's a free. That's my question. So does a hydro actually modify that?
They're not the typical hydro calculation, they don't have this, that stuff in there.
typical hydro evolves.
You need some diffusion in there on top of hydro.
So that means the hydro doesn't change.
Yeah, but if I did some proper fed, maybe by now they have charge diffusion in modern hydro code,
2-point correlation.
and that would do it would help, right? I mean, but so just by hand waving, I mean, it seems to me one has to sort of do some kind of an average, right? It would be very unlikely if everything gets frozen at one point, right?
Yeah, maybe one could also
So
study.
no. My question is even more naive. So suppose I heat the temperature of the quark past
Yes.
600 MeV,
Yes,
and then I use hydro to cool down.
yes.
I mean, if the hydro evolution does not change your charge fluctuation, that will remain there.
But I have I have an external acceptance and I have diffusion out of this acceptance, so it's not actually perfectly. If I had infinitely large acceptance and infinitely bigger fireball, then I could say I freeze it somewhere, right? But in practice, things are moving around, right? So there is a question up there on Zoom.
Repeat?
Yeah, so I have a question about the blast wave model. So when you apply the blast wave model, I assume you just assume the distributions are ideal. I wonder if the viscous corrections could be relevant and if that help us to differentiate different viscous correction models.
So it's a good question, and I don't know.
Yeah.
So we are using just the basic blast wave model, and we assume probabilities for acceptance probabilities for different particle independent.
Mm-hmm.
And about viscous crush, I can't answer.
The blast wave model, the only thing it gives us is acceptance probability. So viscous hydrodynamics, I mean, it was fitted to experimental data in the first place. And so we use it only as a source of realistic single particle distribution. I think it's probably not the best framework to try to constrain viscous effects here.
No, that's right.
But if this P of eta, these viscous corrections could be better than blast wave, which we also know not exactly perfect, then that could be an improvement, I guess.
Okay, thanks.
So regarding the hydro, like in the normal hydro model, right? And if you want to calculate this observable measure, and then you cannot usually get the this expected because at the end, like you switch the description from hydro to the hadrons by sampling, and then so at the end, okay, let's forget about local conservation of the charge, and then maybe you cannot really get the even if there is a QGP inside, you cannot really get the right D measure, right? Because it's
So the main point we here obtaining predictions for QGP and HFG on equal grounds. So if in your model you can switch off QGP phase, switch it on, it will work.
will it work?
Well, if you do hydro and you do Cooper-Fry into a hadron gas,
And then you
you
cannot
get a hadron gas result.
yes, yes, of course.
Because at the moment you do Cooper-Fry, you forget
Yes.
everything about the past,
Yes,
right?
yes, but then if you have the local conservation of the charge, and
That's then the hydro plus local conservation, right?
and then you expect to see this D measure equals 4 or 1, I forgot which one.
No, I mean, one is quark-gluon plus one,
Okay,
right?
okay,
Yes.
one.
Or whatever.
But I mean, if you do Cooper-Fry in the standard way or canonical way,
Yes.
even canonical way is based on the assumption that you reduce to HRG in non-canonical limit. So the physics is always the equal 4 in standard way we do it. Whether we do it, even if we do it canonically, we get canonical effect, the blue curves that Roman showed. But then if you theoretically would correct for this canonical effect, you would go back to 4.
Exactly.
And here the new thing is that we have a model of two-point correlator where during the hadronization process, the 1/3 charge carriers of QGP transform into correlations between unit charges,
Right.
unit charge carriers. And so this is a model of two-point correlator then that we're not sampling it, we're just calculating analytically. I'm actually not sure how easy it is to sample it. So I think, standard hydro essentially is hadron gas scenario only as far as fluctuations concerned, at least to my understanding.
So in a sense, if I run Yuka's code, I would just go back to hadron gas.
You get the blue curve if you correct for global charge conservation.
Other comments, questions? If no, okay. So thanks.